Y ahora nos vamos a la plática de la doctora Megan Horton. Sí. Yes.
Thank you for the invitation from the Academy and from Dr. Telez Rojo. Today I'm talking about, echo? No, it's okay? Okay. I'll expand on the definition that both Dr. Telez Rojo and Dr. Wright gave on the exposome and talk specifically about the neuroexposome and some data-driven approaches and new tools that we're using in my lab that allow us to ask new questions about children's environmental health. As already described, the exposome, in brief, is the measure of all exposures of an individual in their lifetime and how these exposures relate to health. And as I mentioned, I'm particularly interested in the neuroexposome. So this is the brain's distinctive response to exposomic exposures and the impacts on health and disease of the brain throughout the life course. So this is a concept that was introduced by Tamez in this paper in 2022 to focus specifically on how are these exposures in our life course impacting the brain. And again, looking at internal exposures, external exposures, social exposures, and environmental exposures, similar to the way Dr. Wright described them. So how are we measuring these in my lab, and how are we thinking about moving this field of neuroexposomes forward to improve children's health? So as I mentioned, and as Dr. Wright set up so well, this concept of critical windows or early life exposures aligned with the DOAD, or the developmental origins of disease hypothesis. So in my lab, we're very interested in understanding what's happening to the mother and to the child during these critical windows of development very early on when the brain is developing. So I'll talk a little bit about some of the tools that we're using in my lab to measure these exposures early on. The other tool I'll talk about today is focusing on the outcome, or when we're interested in looking at these outcomes. And in my group, we're very interested in looking at adolescent health. Adolescent health is this kicking off time into adulthood, when this critical transition from childhood to who we're going to be as adults. And there's a lot of developmental change in this adolescent period that I'm interested in understanding how early life exposures can set a child on a typical or atypical developmental trajectory. And this is when we can start to see this as an adolescent. So we think it's a very important time to start to look at these phenotypes or outcomes. And finally, I'll talk a little bit about how do we put this together. Now I'll talk about how we have this high dimensional and very rich exposure data and very high dimensional and rich outcome data. We can't just do linear comparisons anymore. It's very complicated. And so we're working with statisticians to try to understand how to put this high dimensional data together and understand how that can improve health throughout the life course. So I can go over this pretty quickly because Dr. Wright introduced the concept of the developmental origins, which in brief is a concept introduced by David Barker in the 1990s or 1980s, where he was one of the first physicians to really look at how he looked at birth records and death records and really linked how a person's experience at birth was influencing their risk for chronic diseases later in life. So he was very interested in nutrition and cardiometabolic diseases, but this concept expanded pretty rapidly to understanding not just nutrition, but understanding all environmental and social exposures, and that this time period very early on in the first 9 months of life and that early postnatal period could have a critical effect on your health over the life course. This is a paper, again, depicting this idea of critical windows. So what you're looking at in this figure is time throughout that gestational period, looking at the embryonic period in weeks. And you can see a little bit, it's not super clear, this is a very old paper, but what you can see is where an organ or a system is developing is when it's more vulnerable. And so if you look at, for example, the development of the ears or the palate, once the ear is developed, it's not as vulnerable to perturbation. So if you were to see a child with cleft palate, they might have had some sort of insult when the palate was developing. And so the idea of this figure and of this paper is try to capture the fact that exposures that are coincident with a developmental process are more likely to cause adverse effects. So in my world, and when we're thinking about the human brain is both the slowest and the most complex to develop. So this is a map looking at the development or developmental milestones in the brain from gestation through birth all the way up through the life course. And these slopes that we're looking at are showing the rapid changes in that developmental trajectory and demonstrating that the growth of the brain is long and slow and dynamic. So we're not just looking at a single slope or a single speed of development, that it's nonlinear. So, and it's going on for a long period of time. So this is again enforcing the fact that if we're looking at critical windows of exposure, the critical windows of exposure for the human brain may last from gestation all the way up through that early adulthood period. However, I want to draw your attention to down here, where this is what the circles are showing, what the big circle and the little circles are showing in this figure is the peaks of development. And so that's when the developmental period is most rapidly changing. And you see that the most of the circles are in this prenatal period and this early postnatal period. So we think that these are very critical windows or susceptible windows to exposure. And the other part of this map that I'll draw your attention to is the triangles. So this is the maximum of the development. So this is sort of the end of that trajectory. And that's when the brain sort of plateaus and our behavior and our phenotype is a little bit more stabilized until we reach the aging period, and then this slope starts to change again. So these are the two periods that I'm very interested in, is understanding how to link this early part of early exposures with these adolescent phenotypes. And so how do we measure that? How do we measure exposures that are happening very early in this time point? Some of our traditional biomarkers may not be effective at adequately capturing exposures during these critical points. Most often when we're studying a pregnant mom or when we're studying a young child, we rely on specimens such as maternal blood, urine samples, and cord blood samples, because these are the easiest to get. It's very hard to get an umbilical cord blood sample or to get, it's very hard to get fluid from the developing fetus. And so if we're lucky, we get a few time points of blood or urine collected from the mom, and we might get cord blood. And then throughout that first period of life with the child, we might get 1 or 2 blood samples, but it's very challenging if any of you have ever tried to get a blood sample from an infant. And so we don't have very good measures that are capturing this critical period. We also know that maternal blood measures may be an indirect and inaccurate proxy for what the fetus is experiencing. And I always talk about this example, in addition to the metals that I'll talk about today. During my career, I've done a lot of work looking at pesticides, and chlorpyrifos is one of the most widely used insecticides in the world. And we did a study where we were looking at chlorpyrifos exposure in the mom and in the developing infant. And one of the things we found was that chlorpyrifos levels that we measured in cord blood at delivery were significantly higher than those that we measured in the mom. So this is suggesting, again, that mom's blood may not be a good proxy for what the infant is experiencing, because the mom has her own metabolic capacity. She may be able to degrade the compounds and excrete them, while the infant is in a very different developmental stage in both its liver and its kidney function, and may not be able to metabolize those. So this is to emphasize that the mom's blood may not, or urine may not be a good proxy. And also, it may not reflect exposure throughout that time course. It's assuming that the 1 or 2 time points that we get, that we're assuming that those are a proxy for that exposure throughout that time period. So with two researchers at Mount Sinai who developed the process of looking at perinatal exposures using baby teeth or deciduous teeth. Children lose 20 deciduous or baby teeth between the ages of 5 and 13 years old. And the critical thing about these baby teeth is that they begin developing in the 2nd trimester of pregnancy and continue growing until the time that the tooth is lost. And because of the physiology of the teeth, and I'll talk about it in the next slide, we can use these sort of like you would use a computer hard drive or the growth rings in a tree. So we can look back on a daily, weekly, or monthly basis and see what that child was exposed to from the time that the tooth began developing until the time the tooth was lost. So this is a schematic of a human incisor, so a tooth, where you're looking at the way the tooth erupts from the gums, and just briefly we're looking at the enamel, the primary dentine, the secondary dentine, and the pulp. So the pulp is where there's blood flow, and what happens first is the development of the primary dentine, which erupts from the gums, and then there's secondary dentine, which is growing after the tooth has erupted. And what's critical in this, and this is again sort of mapping how that tooth is growing, is that at this figure C, at birth, there's a neonatal line formed that we can actually see using the microscopes that we can look at in the teeth. And so when the child is born, there's this formation of a neonatal line, And so you can backtrack and look at the layers of dentine and enamel that were laid prior to birth and the layers that were formed after birth. So it acts sort of as this anchor, so that we can do a timestamp and then calculate pre-birth and post-birth and look in those layers and see what exposures were like. So what Manish, or what Dr. Aurora and Dr. Christine Austin did was use this material to look at metal exposures, first looking at metal exposures, and understand what exposures were like throughout the life course. So this is an ICP-MS map of the tooth, looking at, what I want to draw your attention to is the lead, which is in red up here. And this is a graphic time distribution of that lead exposure, looking at that second trimester of pregnancy through birth and through 200 days of life, and we're mapping those lead levels. And what you can see that is interesting here, and this is a tooth from one of the studies that Dr. Tellez Rojo started, from one of her participants. And what we knew is that the mom did have blood, she did have a higher level of blood lead. And what we see is that we captured that blood lead in the third trimester. So those of you that are familiar with gestation and developmental milestones of gestation, is this third trimester is when that developing infant or developing fetus is really starting to grow. So in the third trimester, there's considerable remodeling of the skeletal and the muscular system. And so that baby is acting very similar to a parasite and just pulling all of the nutrients that it needs from the mom's blood. And so while it's trying to pull the calcium, it may accidentally or incidentally pull that lead exposure. And so that's exactly what we're seeing, is that where there's exponential growth in the fetal skeletal system, that we're seeing that that infant was also absorbing a lot of lead from the mom's blood. So this is demonstrating that if we had measured, for example, gotten a blood sample from this child at 1 year, we might have missed this peak exposure. And this peak exposure may be related with adverse outcomes. So this is just demonstrating that the temporality of understanding not just the information we can get from a single time point, but that cumulative exposure throughout these developmental periods may be important. So we started looking at lead and manganese, and we've now expanded this metal mixtures to look more at, we're looking now at 16 different metals. And so we can look at these, and this is again from a couple of children enrolled into the Progress cohort, just showing, and I don't say which metals we're looking at, but each one of these colored lines is a different metal, and we're looking at that over time, again, from pre-birth to that first postnatal period. And what you can see is a lot of temporal variation, again demonstrating that it's important for us to look at this exposure over time, not just look at a single time point. And this is just a cool GIF of the moving mixture, so you can actually see how those exposures are changing over time. We've expanded this to take a more omics approach, so not only looking at metals, but now Manish can look at parabens and phthalates, PFASs, pesticides, and other compounds that we think are very important. But today I'm really focusing on the metals. So I talked a little bit about the early period and how we're going to measure exposures, and the key to us measuring the outcomes and understanding what's going on in adolescent brain health is to use MRI to really understand a bit more about brain structure and function. So I'll give a very brief tutorial about how MRI works and how we can use MRI to understand typical and atypical development. So MRI scans work as an imaging method due to the unique makeup of the human body. All of our cells are made up of water, which has hydrogen ions, which are positively charged. So this graphic right here shows what our hydrogen atoms look like when our body is at rest. They're naturally and randomly precessing, so sort of randomly bouncing around in our body. When we apply the strong magnet of the MRI, all of those positive ions of the hydrogens align. So they're all going in the same direction. And we can vary the magnetic field to allow those hydrogen ions to precess to their natural state. So what's key to this is that each of the different tissues in our brain or in our body, so our gray matter, our white matter, and our cerebrospinal fluid, they all precess or return to that state in a different way. And so we can look with very fine spatial resolution to see what materials we're looking at. And this allows us to get these maps, such as these T1 maps here, of brain structure. And so what we can do is use MRI to look at the three main different modalities. So we can look at structural outcomes in MRI. So this is the anatomy of the brain, namely the difference between gray matter and white matter. So you can look at volume, thickness, different surface areas of both cortical and subcortical structures in the brain, try to understand how the structures are changing both developmentally and how environmental exposures can change those structures. Another outcome that we use in MRI is called functional MRI. And while structural MRI looks at the anatomy, functional MRI is a proxy for brain activation, or what's happening in the brain when we put the child in or the person in the MRI. And functional MRI is reliant on a measure that's called blood oxygen level dependent signal. So briefly, what this says is that this is a proxy for if a brain area, so for example, right now, my verbal brain regions, a little bit of my motor brain regions, they're working a lot. So they're requiring, those regions of the brain are requiring more oxygen and more glucose, so there's more blood flow in the brain in those areas. So in a state at rest, there's a balance between oxygenated and deoxygenated blood. However, in an activated state, when the brain is demanding to do a task, there's a shift in that balance. There's an increase in blood flow. The deoxygenated blood is decreased as the oxygenated blood is increased, and this signal changes, and we can capture this signal using the MRI. And so what we think we're capturing is a proxy for activation. Most often when this is done in the scanner in the past, this was done by asking the individual in the scanner to do a task. Sometimes to look at motor function, we would ask them to tap their fingers, or we can ask them to do a memory test. So while this is very interesting and very useful in understanding very specific regions of the brain that might be active during a task, this is even harder to do in a child. If any of you have had a child and asked them to lie still for very long, that's a challenge. If you ask them to lie still and tap their fingers, they'll automatically go down and they'll look at their fingers. Or if you ask them to do something, they'll start moving a little bit more. So this task-based MRI was really hard to do in children. So investigators started to look at what's happening with the brain at rest that may inform what's happening with the brain when it's undergoing a task. And they realized that most energy consumption in the brain is related to intrinsic activity or activity at rest rather than to external stimuli. So this sort of revolutionized the way we could look at the proxy for brain activation by allowing a child just to lay in the scanner and not having them do any sort of task. So we can look at activation in different brain regions without having the task. The final modality that I'll talk about today, so we've looked at structural MRI that does brain anatomy, functional MRI that looks at brain function and activation. Diffuser center imaging, or DTI, is a way to look at white matter microstructure. In brief, it's based on the way water flows through myelinated versus demyelinated. Myelinated versus, am I still on? Myelinated versus demyelinated neurons. And so it allows us to look at white matter microstructure and look and see where information is moving through the brain and how connected different brain regions are. So these are 3 different ways that we can look at brain structure and function. So as I mentioned, both the technology of the tooth has advanced our exposure, so we can look at not just single exposures, but multiple exposures. And now we have very dense information on the other side. We're not just looking at a single measure like IQ, we're looking at very advanced and high-dimensional outcomes. So we've worked really hard to try to find ways to pull that together. And one of the things we rely on, one of the tools we rely on, is a statistical method called weighted quantile sum regression, which was developed by Dr. Chris Jennings, who is at Sinai. And one of the things so weighted quantile sum regression allows us to look at a mixture of highly correlated compounds. So in this example, I'm using a bunch of different metals. So we know that we can measure arsenic, barium, cadmium, manganese, lead, zinc, multiple exposures. What we try to do is put those into a single index and look at how that index is associated with an outcome, such as our brain outcomes. And one of the strengths of the WQS is that it allows us to look at, once we look at these factors as a whole, we can backtrack and see what are the heavy hitters. If we have this mixture of environmental exposures, which one of those environmental exposures has the strongest effect on our outcome? Which are the ones that we might want to intervene upon or might be important on a policy level? So WQS allows us to do that. It also allows us to look at both the risk factors and the protective factors. So we can look and see, are these metals neurotoxic, or are there some of these metals in this mixture that might actually help protect against adverse exposures and adverse outcomes? in order to expand to look at that tooth data, right? Because the tooth data now is over time. It's not just a single snapshot of time. So along with Paul Curtin, Chris expanded the method to look at lagged weighted quantile sum regression. So I left the figure of A, the WQS mixtures up here, but lagged WQS allows us to look at mixtures over time. How much time do I have? Okay. So it allows us to look not just at a mixture, for example, in week 1, but we can look at those mixtures for every week that we have a measurement. So week 1, which is that 14th week of gestation, all the way through the first year of life, and look and see, is there one of those windows, one of those weeks that may be uniquely vulnerable, or is there a time period that's uniquely vulnerable? So it allows us to really look at mixtures over time to identify critical windows of vulnerability. And this is what the outcomes looks like. So I'll show you some data from our progress study, but I just wanted to show you that this is a map of time on the bottom, so birth here, again, that prenatal and postnatal period. And what we're looking at is the betas, so the association between the exposure and the outcome at each one of those time points. So finally, getting to a little bit of data, as both Dr. Tellez Rojo and Dr. Wright introduced the progress study, which is an ongoing study that they started in 2006. And I came in about 10 years ago along with Mara, and we started a study to do MRIs on a subset of the kids in the progress study. And I acknowledge several people who are in the audience that made this work possible, because to get a kid to lay in the scanner, as I said, is not easy. But we've now done this for 215 kids. So this is just some demographics of who they are. And we're looking at metals specifically in their teeth. So this is a distribution of the 9 metals that we're very interested in, including some heavy hitters like lead and manganese, and also some metals that may be protective, like copper and zinc, but we don't really know the direction of them. And so what we started to do first was link this mixture with some of those brain outcomes that we talked about, or that I introduced you to. So we looked at how does metal exposure in these critical windows in the developmental period associate with brain outcomes in adolescence. And so we picked total brain volume, so the anatomy of the brain. And what we're looking at here again is that lag WQS model, and we're looking to see where there might be a sensitive window, so where the betas are dropping and the confidence intervals are dropping above or below 0. And it looks like from this figure that there's a critical window in this postnatal period. And if we look at the weights, as I mentioned, we can look and see which metals are driving that. It's manganese, zinc, and strontium in this postnatal period that seems to be driving a decrease in total brain volume. So this is showing us that in these 215 kids, that early life exposure to this metal mixture is associated with reduced total brain volume in kids and adolescents. We applied these to both. I talked about the white matter microstructure, so looking at fractional anisotropy, or white matter microstructure in the brain, and we saw a similar sensitive window in that postnatal period, again driven by manganese, and we saw a window in the prenatal period, suggesting that metal exposure in that prenatal period was also associated with decreases in white matter microstructure, or disrupted white matter microstructure. And finally, we looked at functional changes in the brain, so that activation in the brain. And we saw similar windows, this postnatal period and a prenatal period. So keep in mind that these are prenatal and postnatal periods that we would not be able to capture with conventional biomarkers. So this is really opening up the door to understanding how these critical windows of development may be impacting health later on. We also tried to tie this to behavioral outcomes. So it's interesting to look at the brain, but of course we need to look at brain behavior relationships. So we looked at internalizing and externalizing problems in the progress kids, because we know that behavioral problems like this are associated with adverse health outcomes and adverse lifestyle outcomes, including disruption in employment, in income, in socioeconomic position. So we wanted to see how were our environmental exposures that we saw, these metal exposures, associated with these behavioral outcomes. So we administered a task, or a questionnaire, to the moms and to the children. And we did the same thing, where we used those lagged WQS models to look at how early life metal exposures were associated with behavioral symptoms. And we do see similar windows. So we see this this prenatal window right after birth, and we see this postnatal window right up around 40 weeks, where there was an association between the metal mixture. And when we looked at the metals, there's a lot of overlapping metals. Manganese, again, seems to be a heavy hitter on looking at these adverse outcomes. So in conclusion, I've introduced the concept of the baby teeth that can provide this reconstructed exposure history from the second trimester of pregnancy up through 1 year postnatally. So keep in mind that this was a very hard time period to study what exposures were like before Manish and Christine developed the tooth methodology. One of the things that it allowed us to do is to look at this postnatal period as a critical window. We really didn't know what was happening developmentally. We know what's happening developmentally with the brain, but we really didn't know what was happening in terms of exposures. The other important point or conclusion from this work is that we seem to demonstrate that the association with adverse health outcomes really is a mixtures effect. When we repeated these models with just individual metals, we didn't see an association, for example, between manganese alone and either behavioral or brain outcomes, but we see it with the mixture. So that's demonstrating that these metals are not acting alone. And one of the things we want to do is expand this research to not just look at metals, but to add those other chemical analytes that we can look at now, and also to add the influence of the social environment to look at vulnerability from social exposures as well as environmental exposures. And we think this work really informs both typical and atypical brain development to understand what is typical and when are the most timely and thoughtful interventions to try to prevent some of the adverse health outcomes. So I'll conclude with the acknowledgments, and the list is very long, but of course this work wouldn't be possible without Mara Tellez-Rojo and Dr. Wright in the study, and the huge team in INSP which makes this work, and of course our collaborators at Sinai, and the study participants who have stuck with us now for 16 years and are going to stay for 5 more years, we hope. So, thank you.